Hello friends, welcome to the today's session. Welcome to Unacademy. In this session, we are going to focus on balanced search trees, that is in the part of dynamic multi-level indexing. Last session, we learned about static multi-level indexing. I also trained you how to construct single level indexing to multi-level indexing. In this session, our main focus on dynamic multi-level indexing. So, my dear friends, let us start our lecture. Before that, let us say our anthem. Crack GATE and ESE with India's largest learning platform, none other than Unacademy. Get Plus subscription and access unlimited live and recorded lectures from India's best educators. The caption of Unacademy is nothing but top quality content from top quality educators. Let's crack this. About myself, Srinivasrao, I have having more than 15 years of experience in the GATE. I taught to many batches and thousands of students are relieved and completed their post-graduation from India's topmost premium institutions like IIT, NIT, Central Universities and IIITs. So my dear friends, you also can have such kind of wonderful opportunity to get complete your post graduation from premium institutions. All that you need to do is give your valuable admission to us so that we are going to take care like a parents. So we are here to do parenting. So my dear friends, utilize this opportunity what the Unacademy is providing because without Unacademy you and cannot be in this online platform. So my dear friends, I taught in many premium academies with a high success rate. Many of my students got single and double digit ranks. So you also can have such kind of wonderful opportunity just by taking a subscription in an academy. Once you get the subscription, you are going to be given unlimited access, unrestricted access. Therefore, you can able to watch full content and full courses which are taught by topmost educators. So, my dear friends, apart from that, you also can have a wonderful opportunity to have a maximum concession in your subscription fee. So, use my referral code so that you're going to get a maximized subscription discount. My dear friends, there are two kinds of subscriptions you can opt for. One is a 12-month subscription, the other one 24-month subscription. Current fourth year students can opt for 12-month subscription and remaining second, third and first year students can opt for 24-month subscription. My referral code is eligible for any kind of courses, not only for GATE and ESE. So my dear friends, once you get the subscription, then you are going to have a wonderful content which are already according to the syllabus of GATE and ESE you are going to get. So my dear friends, if you have any kind of a queries, you can come down to us just to fill this particular form at this link. Then Unacademy is going to provide a faculty member who can able to clear your doubts. So my dear friends, it is also providing 1:1 guidance program, nothing but iconic batch. If you take that subscription in iconic batch, then you are going to be given 1:1 a gate coaching. That means all your doubts are going to be cleared with a 1:1 guidance. So let's crack GATE CSE is our Unacademy YouTube channel and subscribe our YouTube channel. Use my referral code and get the maximum benefit out of your subscription fee and hit the bell icon for latest notifications and updates. Now I'm going to present the balanced research trees part 1, which I am going to start with static level multi-level indexing. So what is a static multi-level indexing? My dear friends, you observe the meaning of static multi-level indexing is the order is fixed. When I say that a order is fixed, you cannot able to do increase in the order. That is the meaning of static multi-level indexing. So therefore, what is going to happen as your block factor is fixed? That's what I'm talking. As your block factor is fixed, therefore you have to see that a number of levels are going to be increased whenever you are trying to insert a new elements. So my dear friends, therefore the levels are being increased and hence the height of the tree is going to be increased proportionately to the number of the keys you inserted. So here, the block factor, according to the static multi-level indexing, last session, I kept a question to you. What is the maximum block factor of your static multi-level indexing, such as binary search tree? So the maximum block factor of your binary search tree is nothing but 2. And what is the minimum block factor of your binary search tree is nothing but 0. So my dear friends, according to that, I can able to get what is the height of the tree. If you are concentrating a static level indexing, it's nothing but you can say that the log base 2 because the maximum block factor is a 2 and say that how many number of records you are having. For example, if I'm saying that I have got 1000 records, so how many levels you are going to get if you are using the concept of a base 2, because your maximum block factor is only 2 only. So I can get almost all you are going to see a concept of a 10. So this is the shortcut how you can able to say that the height of the tree and how you can able to say that the maximum block factor of your static multi-level indexing. So the minimum block factor is a 0 and the maximum block factor is a 2. So my dear friends, let us continue. What is the power of your dynamic multi-level indexing? In dynamic multi-level indexing, your block factor is not a constant which can be increased and which can be decreased according to your block size. If your block size is very big enough, then you are going to get your block factor is going to be big enough. If your block size is smaller, then automatically your block factor is going to be smaller in size. But irrespective of your block size, in static multi-level indexing, your block factor a maximum is only 2. But here, I can able to start with a what? You're having minimum block factor, you're also having maximum block factor. So what is your maximum block factor? Which is nothing but m. What is your minimum block factor? According to static multi-level indexing, the minimum block factor is 0. But according to your dynamic multi-level indexing, the maximum block factor is m and your minimum block factor is m by 2. My dear friends, that's why your dynamic multi-level indexing is always balanced, but in static level multi-level indexing, your tree is not 100% assurance that it is balanced. Therefore, you want to have a balanced trees, then there is a requirement of a minimum block factor is m by 2 and there is a maximum block factor is nothing but m. So these are the two questions I put yesterday lecture. That's what is the minimum block factor and maximum block factor of your static and dynamic level multi-level indexing. So my dear friends, so B trees and B plus trees are the special cases of your multi-level indexing. So a tree is going to be formed with the nodes and the top of the node is called as a root and which is having a many kind of a children like your binary search tree only. And they are having internal nodes and you're also having a leaf nodes. So leaf nodes do not have any kind of a childs, but internal node can have a childs and root node can also have a childs. So my dear friends, according to these points, the root node does not have any parents, internal node has a parent, and the leaf nodes do not have any kind of what? Subchilds. That means its block pointers or tree points are going to be nulls, and a non-leaf node is going to be called as internal node. So my dear friends, you observe like this. This is what is the structure of your tree. I'm saying a concept like this is going to be your topmost level is known as a root, and this is going to be intermediate level. It is called as a non-leaf, which is called as internal node, and the last one is your leaf node. If anybody asks you what is the interface to your data file, the interface to your data file is leaf nodes only. What is the interface to the user? The interface to the user is nothing but root node. My dear friends, observe these 2 points. What is that? Interface to the user is a root. Interface to the user use nothing but a root level only. That is a level 1. And interface to your data file. Interface to data file is nothing but your leaf node. So my dear friends, let us see what are the differences between your binary search trees and balanced search trees. So which is the most powerful? Which is the most powerful is a dynamic multi-level indexing is most powerful, my dear friends, because your time complexity is parallelly is going to be reduced according to your block factor. If you are using a binary search tree, then your time complexity is going to be increased even for insertion, deletion, and searching of the node. That's why better you prefer dynamic multi-level indexing. So, what are the main differences between your binary search tree and balanced search trees? So, in your binary search tree, the tree grows vertically. This is one important point. When tree grows vertically, that means you observe that I cannot keep more than two particular childs. I cannot keep more than two particular childs because your maximum block factor is only 2 at every time. Therefore, as you are increasing the insertion of your key elements, then automatically your height of the tree is going to be relatively increased. Therefore, performance wise it is going to degrade because the index block lookups, that's what lookups are going to be increased. So minimum block factor is a 0 and maximum block factor is a 2 because we are talking it is a binary. Now the tree is not always balanced, so binary search tree is not going to 100% assurance that the tree is going to be balanced and the keys are not properly ordered. That's why if you look at the figure here, so there is a chance the tree is here unbalanced. Why the tree is unbalanced here? You observe that this particular node do not have any kind. Otherwise, you say that one node I can have and other node is going to be missed. These kind of problems we are going to have, especially in a binary search tree. And apart from that, it is also suffer a concept called a skew. Skew is nothing but either left side tree is going to be increased or right side tree is going to be increased. So my dear friends, you observe this important point. If you talk about balanced search trees, the balanced search trees, the tree is going to be increased horizontally. What is the meaning? So you look at like this. As it depends upon your block factor. If your block factor is too high, then your tree is also going to be relatively, your sub expansion is going to be done. That means the tree is going to be grown horizontally. So therefore, the number of subtrees to each node and the height of the tree is relatively small. So as you are having the subtree, the tree is grown horizontally, your height of the tree is relatively small. Therefore, I can able to get your record quickly. So the trees are completely based on, especially multi-level indexing. Your tree is always in the form of half full or always in the form of complete full. What is the meaning of half full and what is the meaning of complete full? Complete full is nothing but up to m I am going to fill. Half full is nothing but up to m by 2 I am going to fill. That's why This is your minimum block factor and this is your maximum block factor. So what is the main goal of your binary balanced search trees? The main goal of balanced search trees are nothing but tree is always balanced. And next one is that the keys are properly in order. So the minimum block factor is a seal of m by 2 and the maximum block factor is m. So what is the meaning of m? Is nothing but order of tree. Order of tree is your m. We can also call it as block factor. Now you look at, so B tree and B plus tree are your data structures which are see that every particular a tree which is going to refer as nothing but a what? A block only. So root node is nothing but a one block, internal node is nothing but another block, a leaf node is nothing but another block. So we are going to call them, your particular nodes are in the form of what? Blocks only. So last session I discussed how are you going to get the multi-level indexing. You're going to get the multi-level indexing whenever you require more than one block to able to fit all your index elements. So when you are unable to pack all your index elements in a single block, then there is a requirement of what? A splitting. So that splitting is the concept of conversion of your single level indexing into multi-level indexing. So most of the multi-level indexing are using B trees and B plus trees because insertion and deletion problems can be eliminated. So what is the rule of to insert elements in your balanced search trees? So if the particular node is not full, that means what? There is no requirement of a splitting. Please understand carefully. I can able to maintain a single level. Please recollect last class lecture. I can able to maintain a single level as long as you are having a sufficient space. Whenever the space is full, then you have to go for one more level, that is called your next level. Index on index is the concept of multi-level indexing. So insertion of a node, if that is not a full, the particular block is not a full, then it is efficient, no problem. If at all you see that the block is filled, then you are able to see that there is a requirement of a splitting that particular block. The splitting is the rule of a multi-level indexing because we are unable to pack all your key elements into a single block. Then therefore there is a requirement of a what? A splitting. So split is the concept of multi-level indexing. And what about a deletion? If I am able to delete an element without seeing that, your tree must be half full and a complete full. What is the meaning of half full? Greater than is equal to. What is the meaning of complete full? Lesser than is equal to. This is your half full and this is your complete full. Even I am able to delete an item without disturbing your half full and a complete full, I can happily delete. If you are disturbing, that means what? Tree is not going to get a balanced. Then immediately merge that node with another particular node. So what is the rule? A deletion is a quite efficient if it does not becomes less than half full. So if it is less than half full, then you see that it is going to cause a big problem because it is lesser than your half full, hence that must be merged with your neighboring nodes because we want to see that the tree is always balanced. So this is a very important. Two important rules I said. Insertion. If there is enough space to insert elements, then I don't require any kind of further levels. I'm not going to do any splitting. That's for insertion. If you are exceeding that particular block, then there is a need of a splitting. And deletion. What is the deletion? If you are trying to delete an element, then if the tree is lesser than your half full, that means I am unable to balance it, then immediately you merge that particular node with your neighboring node. Apart from that, it is also offering a concept called rotations. Whenever you have the concept called rotations, I can able to see that a shuffling, I can able to merge them with your neighboring node. So my dear friends, the tree grown horizontally, not vertically. You see that? I can able to see that multiple number of elements I can able to keep in a particular node. Therefore, the tree is going to be grown horizontally and not vertically. So when the tree grown horizontally, then your number of levels or height of the tree is going to be decreased. So what is the meaning of height of the tree? Height of the tree is nothing but a number of levels minus 1. So observe carefully. This is your height of the tree, number of levels minus 1. What is your level? A level is always starts with either 0 or level is going to start with, I am saying that a level is going to start with 1 and height is going to start with a 0. Now let us construct a binary search tree for the following items. Then you will wonder see these many problems are there with the binary search tree. Now I am saying that I want to insert 3. Whenever I am talking a binary search tree, you need to recollect your block factor. This is very, very important. Your block factor is only 2 at every level. Don't forget this. At every level, your block factor is only 2 only. Maximum I am talking, minimum can be 0. Now I am inserting initially 3. So when you are inserting a tree, the tree is a start with a root node, and I am going to insert 14 and 7. So 14 is inserted here and 7 is inserted here. Observe my dear friends. Then I want to insert 1. Then I want to insert 8. Then I want to insert 5. So 5 is greater than 3, lesser than 14 and lesser than 5, lesser than 7. I want to insert 11. I want to insert a 17. So 17 is nothing but it's greater than 3 and greater than 14. So I want to insert 13. So 13 is lesser than 14 but greater than 7, greater than 8 and greater than 11. Now I want to go for 6. So 6 is greater than 3, lesser than 14 and lesser than 7 but greater than 5. So I want to insert 23. So 23 greater than 17. I want to insert 12. So 12 is nothing but greater than 3 and lesser than 14 and lesser than 13. And I want to insert 20. So lesser than 23. So we want to insert 26. And we want to insert a 4. So 4 is a greater than 3, lesser than 14, lesser than 7 and lesser than 5. And I want to insert a 16. So if you observe like this, if you construct a tree like this, then what is going to happen? You see that this is your root and this is your top level. This is the next level and this is your 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 next level. So likewise, what is going to happen? Your levels are going to be increased. So what is the important point here? If insertion of nodes or keys are more, then automatically what is going to happen? The tree height is going to be increased because maximum you can able to keep only 2. And what is going to happen? The lookups, the time complexity to do the lookups is going to be increased. Now this problem you can able to eliminate with the help of balanced search trees. Whenever you talk about the balanced search trees, there are 3 varieties, B and B plus and B star. So here B stands for balanced only. So in this session, our main focus on to B tree only. So what the B tree is telling you, the structure everywhere, entire tree looks very similar. There is no difference among all your nodes. A root node structure is equal to internal node structure. Internal node structure is equal to your leaf node structure. Except that leaf node do not have any kind of a subtree pointers or a tree pointers or a child pointers or a block pointers. But remaining root level and internal node level, you're having a tree pointers or child pointers or a block pointer. So according to that, the structure of your balanced search tree, especially B tree, are completely are same. So why are we using balanced search trees? If anybody asks you a doubt, why are we using a balanced search trees? What is the significance of them? Yes, there is a significance. What is that? It is for vast number of records. So whenever you are having a vast number of records, better you go for a concept of balanced search trees. So whenever your file organization consists of a huge number of records, then the balanced search trees are playing a very important role in order to insertion, deletion, and searching of your element. Otherwise, you can say that the lookups are going to be reduced. So according to that, the structure of leaf node has the same structure as like internal node and root node, except that its block pointers are nulls. So if you assume that, if I am saying this is your, what I mean to say, leaf node, then what is going to happen? Its block pointers, you need to refer them as nulls only, because leaf do not have any kind of subtrees. So that too, the next point is it is an ordered tree. So what is the meaning of order? Order is telling you that you are a block factor only. So maximum order is a m and minimum order is a seal of m by 2. Otherwise you can call it as m by 2 only. So when I am saying that, I can able to have m block pointers. That's the meaning of m. M stands for m block pointers only. When I am saying that m block pointers, so 3 block pointers are there here. I can able to keep maximum is 2 keys. That's what the meaning. When you are having m is equal to 3, I can able to confirm that 2 keys I can able to keep. So m minus 1 keys I can able to do here. And when you are talking minimum, that's very important. So minimum is m by 2. That means m by 2 block pointers you're supposed to sustain in order to that tree is a balanced. And this is about your minimum. And how many keys you can able to keep? So m by 2 minus 1 keys I can able to keep. So if m is equal to 6, so minimum you need to sustain. M by 2 is nothing but 6 by 2 is 3 minus 1. 2 keys you need to sustain. So minimum is m by 2. So what are the advantages? So duplicate keys are not allowed. This is a powerful feature. So you need not maintain what? A repetition. Those repetitions are disallowed, especially in a B tree. But B plus tree, you are having a concept called repetitions. And what are the disadvantages? The number one disadvantage is nothing but data pointers are available completely at the tree. A root level you are having a data pointers, internal node you are having a record pointers, as well as a leaf also you are having a record pointers. Naturally, record pointers must be available only at the leaf because they are the direct interface to your data file. Why to have record pointers at other levels? But B tree is having that kind of a concept that data pointers or information pointers or record pointers are available at every level of the tree. Therefore, the tree is clumsy and overhead is going to be high because you are maintaining a data pointers at every level. So that's the point. So in B tree, every node has a search key and record pointer and block pointer. Because of this, there is a overhead. So record pointer is associated along with your what? Search key at every level. So we must use the advanced B tree concept, that is nothing but B plus tree, to minimize this overhead. So record pointers are existed at every level of the tree. So there are 3 to 4 important conditions are there for your B tree. The first one is root node. The second one is internal node, nothing but non-leaf node. The third one is a leaf node. What are the constraints? It is mainly talking that minimum and maximum, nothing else. Only constraints for minimum maintenance and maximum maintenance. First one, a B tree starts with a single root node. Observe, that's called level 0 or level 1, whatever it may be. So, which is also a leaf node. Observe carefully. Because whenever you are maintaining a single level indexing, please observe carefully. There are no other levels to me. So myself is going to refer as a root and myself is going to refer as a leaf only. Observe carefully. So I want to give a clarity here. Please see, this is your data file. Whenever I say data file, please recollect my file structure lectures. Since first of this month I have started this file structure concept. Please go through that. You are going to understand all minute basic topics are covered in that. So please refer almost all 4 lectures I covered in file structure so far. Today is the 5th lecture. Now observe carefully. There are some keys. Key A and key B and C and D and E and F. So I am creating index. Why to create index? Because of fast lookup. You want to see that faster access, then there is a requirement of index. If I am following a single level index, observe my dear friends carefully. If I am following a single level index, I do not have any more levels. So I am having index file here. So this index file consists of all your keys. So as there are 6 keys are there, I am maintaining a 6 keys if I am using the concept of a dense. If it is a sparse, I am maintaining only 3 index keys, only that ACE only. So observe carefully, there is a pointer. So every record, there is a pointer. Use the pointer, get the record. Use the pointer, get the record. So use the pointer, get the record. Those pointers are called record pointers. Observe my dear friends, record pointers. So use this pointer, get the record. And use this pointer, get the record. And use the F record pointer and get your record. So I do not have any further levels. Why? You may ask me a doubt. Why are you not maintaining a tree structure? Because there is no necessity. Why there is no necessity? All my keys, index keys, are sufficient to fit in the single block. Observe carefully. As long as you are maintaining them in a single block, there is no concept of a splitting. You are having a root and itself is a leaf node to you. My dear friends, that all depends upon your block factor. If I am saying that my block factor is a 10, I can keep 10 elements. As long as I am not exceeding my index block, which is not greater than 10, there is no requirement of splitting. I can maintain a single level indexing only. When you increase or when you exceed this 10, then there is a requirement of what? Splitting of node. When you split, then some of the elements goes to the root and the remaining elements we will call them as a root. Remaining elements we are call them as internal nodes, otherwise the leaf node. Please get my point. This is very important. Why to do balanced search trees? Why to do binary search trees? Why to do multi-level indexing? Why to do multi-level indexing? If I am unable to keep all my entries in a single block, then there is a requirement of a splitting. This splitting causes you multiple levels. So that's what. What is the point? So tree starts with a single root node, which is your leaf as well as root. So now the splitting is begin. What is that? The root node has to have minimum of 2 3 pointers. So whenever you talk a root, it's supposed to have 2 3 pointers. When I am saying the 2 3 pointers, then I can able to insert only one key. Observe carefully. So these are your child pointers, also called as a subtree pointers, also called as a block pointers, especially in RDBMS. We have to call them as a block pointers only. And maximum I can able to have M or P. So complete full and half full. If you look at the second point, he's talking about the middle nodes. That's called internal node. Internal node is supposed to have minimum of p by 2. This is for root. A root minimum 2, but internal node minimum p by 2 or seal of m by 2. And maximum you can able to have m block pointers complete full. This is, and the first condition is half full. The second condition is a complete full. Now the last point is for leaf node. What is that leaf node? So minimum seal of m by 2 minus 1 keys and maximum m minus 1 keys. So all leaf nodes are at the same level. And leaf nodes have the same structure as your internal nodes, except that the tree pointers are nulls. So I will show you how to construct your B tree as completely different from binary search tree and completely different from B plus tree. So B tree has got its own significance because duplicates are disallowed in this. So what is the equation to find the degree or order of your B tree? Before that, let me construct so that you will understand what exactly this equation meaning. So I'm constructing B tree. First, let us construct a maximum tree representation. So let me give the keys. If I'm saying 10, 5, 7, 1, 15 and 20, you may ask me a doubt. Sir, why are you not repeating? Why are you not repeating index keys? Observe carefully. You may have a doubt, why are you not repeating index keys? So there are few varieties of indexes I said. Primary index, cluster index, secondary index. Please recap my previous lectures on file structure. Primary index is created on primary key. Cluster index is created on unique values. And a secondary index is created on a key. See, please observe carefully. That means, what do you understand? Primary key do not allow duplicates. And cluster index is only unique values, no duplicates. Secondary index, it is created on a key, no duplicates. When I say that secondary index is created on a non-key, then you talk about the concept of what? Duplicates. Unless and until you don't find any kind of a duplicate insertion of elements in your index table. Observe, my dear friends, carefully. Observe this is a very important point. Why I am not maintaining duplicate keys in your indexing table? That means because index is constructed on either primary key or index is constructed on unique values or index is constructed on secondary index, which is nothing but a unique key. Whenever I am saying that secondary index, it is a unique key only. Keys are and must not have duplicate. But when secondary index, there is a provision you can create on a non-key, then we need to insert a concept called as what? A duplicates. Now listen. So you want to construct a B tree. In binary search tree, the maximum block factor is a 2, but B tree is not like that. That depends upon your M order or block factor. Now I am telling you, let block factor is equal to 4. What is the meaning of a 4? Which is nothing but M is equal to 4. What is the meaning of m is equal to 4? I can say that 4 block pointers, 4 block pointers in a single block. Observe carefully. In a single block, I can able to maintain 4 block pointers. Now tell me, my dear friends, is the tree require multi-level indexing or single level indexing? Observe carefully. Answer my question. Otherwise, let me erase this point. What is that? I will erase block pointers. I want to say as 10. When I am saying that m is equal to 10, now tell me 10 block pointers. 10 block pointers at a time you can able to insert in your single block. Now tell me, my dear friends, are there requirement of multi-level indexing? This is my question. Is there a need of multi-level indexing? We will say no. Why? Because all the 10 elements 1, 2, 3, 4, 5, 6, only 6 elements are given to you. So I can able to fit in a single block. When you successfully able to fit all your elements in your single block, then there is no requirement of any kind of levels. No splitting is required. So single level indexing is sufficient. Now, if I am saying your index keys are 10, 5, 7, and 1, 15, 20. Now, these are your index keys. Now, I am giving you your block factor is equal to this time 4 only. So, what is the meaning of a 4? The meaning of a 4 is nothing but 4 block pointers at max. Now you see, I need how many levels? This is your question. How many levels required? If I am using binary search tree, what will happen? If I am using binary search tree, what will happen? If I am using balanced search tree, that is a B tree, how many levels? If you are talking balanced search trees, you know how to find them. A log of 7 keys are given to you. And what is your base? 4. And according to your binary search tree, log of 7 keys are given and base is 2. So according to that, there is a requirement of 3 levels. And according to this, there is a requirement of 2 levels. Observe carefully. So this is how you can simply say your answer using this shortcut trick, and no need to construct it that how many levels you are going to get. Simply using this equation and say that how many levels you want. But you will ask a second question. What is the question? How many block access to search a record? How many block access to search a record? To search a record. Last session I gave you this trick, my dear friends. What is that? So you find number of levels to index file, and you need to add +1. This is a mandatory. So according to the previous question, if it is a binary search tree, 3 levels, please observe carefully. According to your binary search tree of your previous example, 3 levels, and you need to add +1 to search your record, that is nothing but 4. According to your B tree or B plus tree, dynamic multi-level indexing, I can say that 2 levels required and +1 is a mandatory. So therefore 3 altogether. Why +1? You may ask me a doubt. Those who are listening for the first time today, you observe why there is a need of a +1. Exactly, there is a need of a +1. Now you tell me, according to this question, how many block access to search a record according to this example? To search a record according to this example, so user wants to search F, assume. I want to search F. So he type F in Google search, you talk in Google search. When I say that F in your search bar, it starts searching. So F found here. So only one level only. Observe that. One level plus one level to get back your data from your data file, +1. Always +1 is required to get back your data to your data file. That's why +1 is a mandatory whenever you talk a concept called as a what? Indexing. Now he is asking you to construct a B tree for this. So 10, 5, 7, 1, 15, 10. Let me construct first a binary search tree. So first I will insert 10, then I will insert 5, then I will insert a 7, then I will insert a 1, then I will insert a 15, then we will insert 10. So if you are using the concept of primary key, so you need not insert this 10. Observe carefully. If your index is built on primary, that is a primary index, or if your index is created on a cluster, it is a cluster index, or if your index is created on secondary index, especially secondary index has got both options, key and non-key, then remove that 10. No need to insert that 10. Then you are having only 6 keys only. So if I am talking your B tree concept, I said m is equal to 4 according to the previous example. Take a one block and you see that there are 4 child pointers I can maintain. This is a one child, 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 because a tree can grow horizontally. Now 3 keys I can able to keep. So the beauty of your multi-level indexing, especially B tree and B plus tree, is your keys are properly ordered. So when you are saying that I want to insert three elements I can able to keep. When you want to insert 3 elements, so you please arrange them in a proper order. 10, 5, 7. They will be shuffled as 5 dot, 7 dot, 10 dot. This is your block pointer and this is your key. So 3 elements are there in that. This is your record pointer. Observe carefully. So block pointers are there, record pointers are there, and the key is also there in your single block. I'm talking this is your block 1. Now insert number 1. So 1 I cannot able to pack in a single block. Now there is a requirement of what? Multi-level indexing scheme. So insert 1. So when you insert a 1, it becomes 1, 5 and 7, 10. So which is greater than your 4, because of 5 block pointers you got, you are unable to insert that next insertion, then there is a requirement of a splitting. So the middle element is going to split it. That means it is going to be a root to you. So I have got a 7. So one block pointer left side, it is separated 1 and 5. And the second block pointer is a right side. So we are having a 10 and a dot here. So 1 dot, 5 dot. Observe carefully. This and this is separated with your pointer. Now left hand side block name is block 2. I am labeling them. And right hand side block is your block 3. And root is your block 1. So 3 blocks required right now. So I want to insert 15. 15 is greater than 7 and greater than 10. So when I say that m is equal to 4, I can maintain maximum of 3 keys. So I can keep m minus 1 keys, which is nothing but 3 I can keep at every block. So this block has got only 1 key, so I can able to insert a 1 more key here. What is that key? It is a 15. So let us write here. Already 10 is given according to the earlier. Now 15 is added in this. Plus. So how many levels you got? 2 levels. So instead of doing such a long process, I already gave you a training. What is that? You want to find the number of levels, use like this. What is that? Log base 4 to your number of keys. So you will get 2 levels only. So here log 7 base 2, there is requirement of what? 3 levels. Have you got 3 levels? Let us see. So this is your level 1 and this is your level 2. Exactly, you got 3 levels. This is your level 3. Instead of doing such a long process, you can able to say using that shortcut trick. Okay, down what is there? Down your data file is there. So your data file consists of elements. What is that? 1, 5, 7, 10 and 15. Because why I have written in your data file in a sorted order, you all have to get a doubt here. Why have you not written these elements in the same order in your data file? Exactly. What is that? Your primary index is ordered index. Your cluster index is ordered index. Please observe carefully. Your secondary index on a key is a ordered index. So whenever I am talking that it is ordered index, your data file follows the index order. Whatever the order you are having, there is a record pointers everywhere. Don't forget that. There is a record pointer, there is a record pointer. So use the pointer, get the data. Use the pointer, get the data. Use the pointer, get the data. So use the record pointer, get the data. Use the record pointer, get the data. If user asks, I want to search record number 7, okay. So it comes to the root. 7 less than 10, it comes to the level 2. So 7 greater than 5, it comes to the level 3. Exactly, you got 7. So using the pointer, it tried to get back your record. Now how many levels you have used to access your record? 3 levels from your indexing, 1 level from your data file. Here also, there are 2 levels. This is your level 1 and this is your level 2. And down you are having a same like data file. And record pointers are available at every level of the tree. It is very similar to binary search tree only, no doubt. But except that the tree grown horizontally because you can able to sustain m keys. This is the simple difference between binary search tree and B tree, remaining everything is same. Now you observe carefully, we got 2 blocks, 7 in your root level, so this is your B tree structure we have constructed. There are 2 child pointers called as block pointers. Now left side we have got 2 elements, 1 dot 5 dot there are 2 pointers here and here, and you see that this is having 2 keys, that is a 10 and 15. Now there is a down data file. So this data file is telling you that the keys, because your data file is ordered, because your index is a primary index, means it is a data file is also ordered only. So whatever the order you are having, B trees and B plus trees are completely ordered index only. So we have got this is a 1 5. So we have got 1 5 and 7 and 10 and 15. This is the beauty. Now use the pointer to get back your record, and use the pointer to get back your record. So tree pointers and record pointers are available at every level of the tree, as I told you. This is your leaf and this is your root. The root also has got data pointer along with your leaf node. That's why leaf node structure is equal to internal node structure is equal to root node structure. My dear friends, how many levels you have to access the record? I already told you, to access a record, you see that number of levels in your index are 2. This is your index path. 2 levels plus 1 level is required to get your data from your data file. Now you tell me, this is your block 1 as a label, this is your block 2 as a label, this is your block 3 as a label. I am going to represent now horizontally. Observe carefully. So first you are having your data file. Observe, my dear friends. Your data file consists of the following records: 1, 5, 7, 10, 15. Now you tell me, we have created a block 1. Observe carefully. And we have created 2 sub-blocks, block 2 and block 3. Block 1 consists of, observe my dear friends carefully, 7. Block 1 consists of 7. It has got 2 block pointers and it has got record pointer 2. Now you see, this is referring to your block 2 and this is referring to your block 3. Please observe your previous diagram. So I have given there vertically, now I am writing horizontally. This is referring to block 2 and this is referring to other block 3. Now your block 2 has got few elements, 1, 5, and your block 3 has got few elements, 10 and 15. And this is having block pointer, no doubt. This is having a block pointer. Every block require a block pointer and block pointer. I do not have any further referencing. Therefore, they are nulls. Therefore, they are nulls. Right hand side block pointer is null. And this pointer is also null. Now observe carefully. 1 dot, 5 dot, 10 dot, 15 dot. What are they? They are your record pointers which is trying to get back your data. So 2 parts. Your index has got 2 parts. Please, already I told you in the previous lectures. Whenever I am saying that index has got 2 columns. One column is a key and the other column is a pointer. So here also I am maintaining 2 elements. So one is a key and the other one is a pointer, and one is a key, the other one is a pointer, and one is a key, the other one is a pointer. But especially we are having a block pointers too. Three elements are there. Now this 7 is referencing this. This 1 is referencing this. This 5 is referencing this. This 10 is referencing this. This 5 is referencing this. This is what exact structure of your B tree. This is how it is going to be done. So how many blocks you have consumed? I have consumed 3 blocks for indexes and 1 block for data file. Observe carefully. 3 blocks for index file and 1 block for data file. You may have a doubt, why have you used only 1 block for a data file? That depends upon your data file block factor. Please recollect previous lecture, how to find data file block factor. How to find data file block factor? You know that. So how to find a block factor of index? How to find a block factor of data file? According to that, it decides how many data records you can keep, how many index records you can keep. If I am saying that your block size is equal to 1024 bytes and your data record size is 100 bytes, I can keep 10 records maximum. This is about data file block factor. How to decide how many blocks you need. So if you are talking index size, index block factors, then again same rule we follow. What is that? 1024 your block size. You need to write here this time index block size, index record size. So the first one is your data record size and the second one is your index record size. So according to that, it is going to tell you that how many records you can able to keep in your single block. So come to the point. What is the B tree block structure? B tree block structure. Every block, if you consider, every block has the following 3 elements. One element is a key and the other element is a record pointer and the other element is a block pointer. Please observe, this structure is B tree block structure is the same for leaf and B tree block structure is same for internal node and B tree structure is also for root node also. So if you look at the previous diagram, you will understand. You will have a key value, you will have a record pointer, you will also have a block pointer, this arrow. These are nothing but block pointer. So 3 elements we are able to coop up in a single block. So if you understand, you take a 1 block, this is your block, which consists of block pointers, which also consist of keys, which also consist of record pointers. 3 elements are there, block pointers, keys and record pointers. These are all available in your block. So what must be the block size? That depends upon these 3 elements. What is your block pointer size? What is your key size? What is your record pointer size? Then I can able to see that what may be the block size I required to able to store all the 3 elements. Now my dear friends, that is the structure of formula. What is the formula? Come to our slide. This is, so your B tree has got block pointers and keys and record pointers. They are all supposed to be available in your block only. So maximum representation I am talking. When you are talking a maximum representation, you please recollect your M. So M is nothing but your order. This is also, you can call it as a P. Now how many keys at a time I can able to keep? How many block pointers at a time I can able to keep? That depends upon this. I can keep a maximum m block pointers. M is equal to 5 means I can maintain 5 pointers. So 5 pointers means I can keep 4 keys only. And every key is associated with a record pointer. Therefore, there is a requirement of this. This completely available in your block. So this is the equation of your B tree. What is that? M block pointers, M minus 1 keys, M minus 1 record pointers supposed to be available in your block. B is nothing but page size or a block size. N is nothing but block factor are called as a order of your tree. Key is nothing but a key value. PR is nothing but your data pointer. Please remember this equation. What is that equation? M block pointers, M minus 1 keys, M minus 1 record pointers are fit in your a single block. So let me give you a clarity on maximum representation. This is very, very important, my dear friends. When I say maximum representation, level 1, maximum nodes 1. So let me give you the block also here. Only one node at level 1. And if I am saying that P is your order, I can have maximum of P block pointers. If I say P is equal to 5, I can have 5 block pointers. When I say that I have 5 block pointers, I can keep 1, 2, 3, 4 keys. So, and these block pointers are going to be the next level nodes for us. Every subtree, every block pointer is going to create a subtree. This is a one subtree, this is another subtree, this is another subtree, this is another, this is another. If it is a binary search tree, you are having only 2 subtrees for every level, left and right. But here you can have m subtrees according to your order of your tree or block factor of your tree. So next level you will get those many nodes, p nodes. And how many block pointers? This is having a, once again a p block pointer, this is having a p block pointer. That's why p square block pointers you will get. And number of keys are nothing but p into p minus. And when you come to next level, your maximum number of block pointers are p squared. And your block pointers are p cube. This is your maximum number of nodes. Your keys are p square and p minus 1. At last, this is what is your situation. Now I will show you the maximum representation with one example. So level, next one is maximum nodes, maximum keys. Maximum keys and maximum pointers. So level 1, observe carefully. If I am saying that m is equal to 5, that means 5 block pointers you can say, maximum 5. How many keys? 4 keys. It starts with the root node only 1. So these 5 pointers at level 2 becomes a 5 blocks to you. And you have 5 square pointers. And every subtree is going to store 4 keys, m minus 1 keys. When you look at level 3, these 5 square are going to be your nodes. And you will get 5 cube pointers. And you will get 5 square into each is going to store 4 keys. To imagine at level 3, maximum keys. At level 3, total keys, total maximum keys is equal to 124. 4 is here, 20 is here, 100 is here. So how did you get this? I will show you a shortcut. If levels are 3, if levels are 3 and the order is 5, dash maximum keys, total maximum keys in B tree. I can say our answer is very simple. Is that number of levels and your order is 3 and minus 1. Your order is 5. So your order is a 5 and number of levels 3 and minus 1. So 5 into 5 into 5. It is nothing but 125 minus 1. So you got 124 keys. So what is the answer? Your answer is M of L minus 1. So using this, you can able to get the maximum total number of keys. According to the previous example, we get the same. So we got 124 keys. How did you get this? It's a very simple. I will show you in the diagrammatic representation. First, you talk about the root. The root can able to maintain 5 block pointers because I said M is equal to 5. So this has got one tree. This has got another tree, next level. 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 Now you tell me, level 1, you are having only one node with a 5 block pointers. Only one node with a 5 block pointers and 4 keys I can able to insert. Key 1 and key 2 and key 3 and key 4. 4 keys, 5 block pointers, only one node. It's perfectly alright. When you talk about level 2, level 2 also can have same maximum filling now 5 block pointers. Every child can store 5 block pointers. So 5 block pointers, how many keys? 4 keys. And here also 5 block pointers and 4 keys. 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 Now you tell me how many block pointers you got at level number 2. So 5 and 5 and 5 and 5 and 5, 25 block pointers. Pi square, which is nothing but p square. So how many keys you will get? Every particular block can able to store how many? So 5 nodes you got. Every particular block can store 4 keys, m minus 1 keys. So 4 and 4 and 4 and 4 and 4. 5 into 4 is nothing but 20 keys. So 25 block pointers and 20 keys. So that is satisfied at level 2. Level 3 also same. 5 square your nodes, 5 cube your block pointers, and every node, 5 square nodes can able to store 4 keys. So altogether 124 keys you could get. Now you observe minimum representation. So it is half full. Maximum representation means a complete full. Please understand, my dear friends. Maximum representation is nothing but complete full only. And minimum representation is your half full. So this is awful. Now level 1, minimum number of nodes 1. So it is a bit confusion. Don't get confused. Very, very important. It will ask a question. How many minimum number of keys? How many minimum number of pointers at so and so level? We need to be very, very careful to do this answer. And at level 1, 2 block pointers. So when there are 2 block pointers, only one key is available. And at level 2, these 2 block pointers becomes 2 nodes. And 2 into seal of m by 2 pointers you need to maintain, because please observe carefully, your minimum filling is m by 2. So you need to have seal of 2 of, because 2 particular subtrees you got. So every node is going to give you seal of m by 2 minus 1 keys. That is about level 2. And level 3, these 2 by 2 will become your nodes, and you will get 2 p by 2 square block pointers. And 2 of p by 2 your nodes so far, and every node is going to give you seal of m by 2 minus 1 keys. Keys is always minus 1. Don't forget that. And it goes on. So I will show you minimum filling now. Let us say m is equal to 5. He is asking minimum filling, not maximum filling. This is very, very important question. This is, he will ask minimum sometime. So let me go with this construction. First you take half full. Half full is nothing but, you know the rule. What is that rule? Seal of upper value m by 2. So it is nothing but 5 by 2. It is nothing but 2.5. We need to take upper value, that is 3. So 3 block pointers at any cost you need to maintain. And m by 2 minus 1 keys you need to maintain. So 3 minus 1. So 2 keys you need to sustain at every level. So 3 block pointers and 2 keys. Maximum means 5 block pointers and 4 keys. So minimum. So 3 block point. First initially root now. Come to root condition. What is the root condition? Minimum 1 node, minimum 2 pointers and 1 key. Please take this table as a screenshot. Minimum filling and maximum filling. So only 1 node. So 2 block pointers and only 1 key. And second, internal node. This is level 1. Now I am talking level 2. You got 2 blocks. You need to maintain 3 block pointers without doubt, because it is half full. 3 block pointers you need to maintain. So when I say 3 block pointers, obviously we'll get 2 keys. Key 2 and key 3, key 4 and key 5. Next level, level 3. You will get one more block which also need 3 pointers, which also need 3 block pointers, which also need 3 block pointers. And here also 3 block pointers. Here also 3 block pointers. Those who are learning first time, observe carefully. 3 block pointers. So when I say to 3 block pointers, you can sustain 2 keys mandatory. 2 keys here, 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 2 keys here. Now let us come back. So level 1, only 1 key, 2 block pointers. Sufficient or not? Yes, only 1 key, 1 node, 1 key, 2 block pointers. Come to next level. Let us go to our tree. Then we will compare with this. Level 2, you got two blocks. This is your block 1, block 2, and block 3. So you need to get two blocks. Did you get two blocks or not? Come here. 2 into p by 2 pointers. And how many blocks? Two blocks. So two nodes you got. And how many pointers you need? 2 into p by 2. P is nothing but, already we confirmed, half full. Half full is nothing but m by 2 only. So according to there, your m by 2 is 3. So 2 into 3, 6 pointers. Have you got 6 pointers? Yes. 1, 2, 3, 4, 5, 6. How many keys? 4 keys. That is cross check. 2 blocks, 6 pointers, 2 into 3, and 2 into m by 2 minus 1. M by 2 minus 1 is nothing but, I already gave you 2 into 2, which is nothing but 4 keys. So it is satisfied. 1 key here, 4 keys here. Come to level 3. What is level 3? How many blocks? 1, 2, 3, 4, 5, 6. 6 blocks, which is nothing but 2 into p by 2 blocks. 2 into p by 2 blocks. This one I am carry forwarding here, nothing else. How many block pointers? 2 into, already half full, square. So those many block pointers you supposed to get. How many block pointers? 1, 3, and 3, and 3, and 3, and 3, and 3. 6 into 3, 18. Have you got 18 or not? 2 into 3 square. 3 3 is a 9. 9 into 3, 18. It is also correct. So how many minimum number of keys required at level 3? That's very, very important. So 6 blocks, and each block is storing 2 keys. Observe. So 6 into 2, 12 keys we need. Have you got 12 keys? Let us see. So 2 into p by 2 is nothing but 3, and p by 2 minus 1 is nothing but 2. So 3 into 2, 6, 6 into 2, 12. Exactly. So at level 3, how many keys you got? 12. And the summation from level 1 to level 3, 12 plus 4, 16 plus 1, 17 keys. Have you got 17 keys? Exactly. So here 12, here 4, here 1. We got 17 keys. This you can also get using a shortcut. What is the shortcut? M by 2, L minus 1, and minus 1. So m by 2, already we confirmed. How much it is? 3. And L minus 1, 3 levels. What are total minimum keys? He is asking minimum only. Total minimum keys for up to level 3. Up to level 3. So here level is 3. So 3 minus 1 and minus 1. What is your answer? So 3 square minus 1. So what is your answer? So your answer is going to be 3 3s are 9, 9 minus 1, it is 8. So our equation is how much, my dear friends? Our equation is a 17 keys. Up to level 3, the total minimum representation is a 17 keys. Therefore, there is a requirement of 2. So 2 into m by 2, L minus 1 minus 1 is your answer. So 18 minus 1 is nothing but 17 keys. So this is how you can get the minimum representation and the maximum representation. Very, very important question they are. It is nothing but m of L minus 1. M is a 5 there. M is equal to 5. Half full is M is equal to 3. We see that. So 5 of level 3 minus 1, it is 124 keys. Complete full means 124 keys. Half full means 17 keys. Exactly at level number. Okay, my dear friends. So that's the minimum filling and maximum filling. So this you can also represent like this. Minimum representation is 1 plus 2 into your m by 2 L minus 1 and minus 1. You can also do like this. So maximum keys I already shown you, M of L minus 1, and the minimum keys you can also follow like this. So we will see the practice questions in the next session. You please understand carefully today what we discussed. We discussed how to do the splitting in B tree. How to do the splitting in B tree? The split rule is, if you are able to keep all your elements in your single block, then there is no requirement of multi-level indexing, even B tree also. When there is a need of a splitting, when your keys are exceeding than your M. If keys are greater than your M, then there is a requirement of a split. What is the split rule? The split rule is ceil of M by 2. What is a M here and there? M is nothing but order of B tree. This is what we learned. If there are no splittings, your tree is a single level indexing, that is only root, that is only your leaf. And we also learned B tree equation. What is the B tree equation? To get M block pointers and M minus 1 keys and M minus 1 record pointers. These are all supposed to be kept in your block. This is your equation. So using that, I can find a block size, or I can find a key size, or I can find a record pointer size, or I can find M value. You will ask M value always in the exam. What is the order? M is nothing but what is the order? Or sometime you may also ask you, what is the maximum filling? What is the maximum filling? The maximum filling is a M. If you ask that, what is the minimum filling? Tomorrow we will learn all these things, don't worry. What is the minimum filling? Already I trained you. What is that? Ceil of M by 2. Okay friends, please watch this lecture once again, because a single lecture it is not possible. Before watching this lecture, please watch from October 1st onwards lectures. 1st, 2nd, 3rd, 4th, 5th. Then you will understand why we are learning index and why we are, what I mean to say, learning multi-level indexing, why we are learning B tree. And tomorrow we are going to discuss the continuation part of your B tree and B plus tree in tomorrow's lecture. So tomorrow also the scheduled time is 8 p.m. only. Tomorrow we are going to learn balanced search trees part 2, which is the continuation of your B tree and B plus tree. Discuss in tomorrow's session. Thank you very much friends. Please share all these videos to your friends. So our channel is Let's Crack GATE ESE, and there you are going to find me as Srinivasarao playlist. So if you enter into Let's Crack GATE ESE channel, then you will be able to find my name, and I kept lectures, DBMS and operating system and computer network. So far, please watch them, and before coming to tomorrow's lecture, please watch October 1st to October 4th lectures, including October 5th also. Thank you very much friends. Please give me like, and if you want to have still much depth of knowledge using tips and shortcuts, please join in Unacademy, so that you are going to be given extraordinary content which is beneficial towards your end of the life. You can easily crack any kind of examination. So Unacademy is providing a good online platform so that the top quality educators are coming here to give you the top quality content. All the things are going to be under shareable. So my dear friends, trust Unacademy. Unacademy is going to take a parenting, so that it is going to 100% assurance that you can easily crack your competitive examinations like GATE and PSUs and campus interviews. Stay tuned to Unacademy and stay tuned to Srinivasrao Sir classes. We will meet in tomorrow's lecture. Thank you very much.